Okay, so what we're going to do today is go back to basics, in a sense, in that we've, over the last few weeks, been looking at fairly complex stuff, but we're now going to go back to the basic issue of finding proof systems for reasoning with logic. We've already seen one proof system in this course, namely the Hilbert system from, I don't remember exactly which lecture, but one of the early lectures. And today we're going to, and also next week, we're going to look at an alternative, which is called sequent calculus. And this was due to Gerhard Gentzen from the mid-1930s. Around the time Gödel was proving his results, Gentzen was developing his approach to proof systems for logic. So at the time we did the Hilbert proof system, I already mentioned some drawbacks of the Hilbert proof system. One of them you will have experienced for yourself, which is it's quite hard to find proofs. If you need to prove something, the proofs get very long and complicated. So sequent calculus provides a completely different style of proof system. I've got a tape in the notes. Oh yeah, I should say, so there will be handwritten notes for today's lecture, but they're not quite ready yet. So that's why I didn't put them up on the web page beforehand. But I hope to complete them as soon as possible. The last bit of the lecture may involve some improvisation in proofs, and then that improvisation will, in a corrected form, get into the lecture notes that will be online, I guess. So let's actually wait to see what Gentzen sequent calculus looks like, and then we'll do the then we'll compare it to the Hilbert system first. So after that. So Gentzen sequent calculus, it's called sequent calculus because the unit in a proof is a formula. A proof is a sequence of formulas, and so our inferences work on formulas. Gentzen's nice idea was to make the unit in a proof a bit more complicated, give it some structure, and then you can use that structure in order to basically deal with logic in a very nice, elegant way. And that structure, that's what are called sequents, are the structures that the sequent calculus system is based on. So sequent calculus SC provides rules for manipulating something called sequence. And for us, a sequent is simply a pair of finite sets of formulas. This course is a pair of finite sets of formulas which we write like this, written, I'll typically use gamma and delta for finite sets of formulas. I write gamma on the left and delta on the right. And this symbol here is just, for me, a long double arrow. You can think of it as a kind of implication, if you like, but it's not a logical connective. It's simply notation for the pair construction, that we're constructing a pair of finite sets of formulas. In Gentzen's original system, he wrote that with the tone style there, but we already have other meanings for the tone style. So enough thick symbols are overloaded as it is. And the point is, this is simply a syntactic construction, a construction of a pair. Another difference in Genson's original approach from the 1930s was that he did not consider finite sets of formulas, he considered finite sequences of formulas. And you can perfectly well do that, but if you have finite sequences of formulas, you need additional rules that manipulate sequences so that you kind of can identify them as if they were the same, two different sequence representations of the same sets, that you can manipulate them in the same way. So you need additional rules for that. Rather than sets of formulas. That's particularly important in other kinds of logic. For example, there's a kind of logic in computer science called linear logic, and for linear logic, it's really essential to use multi-sets of formulas. But for us, we're going to be dealing with classical logic as we have been throughout the course, and so for us, finite sets of formulas are okay, and a sequent is just a pair of finite sets of formulas. And we'll typically write a sequent either in this form, using gamma for the formulas on the left and delta for the formulas on the right. Or if we want to expand it in terms of the formulas, we're simply going to write a list of formulas. So we're going to write the sequent as though we have a sequence of formulas on the left and a sequence of formulas on the right. Use the set of these formulas paired with the set of these formulas. And we're going to use other similar notations. So actually, a special case of this is with when either n or m are empty, zero, in which case we just don't write anything, and it means that we have the empty set on whichever side is empty. Other similar shorthands are, if gamma's a finite set, we're going to write gamma comma a for gamma union singleton a. And we're going to write, if gamma and delta are finite sets, you write gamma comma delta for gamma union delta. So it's just nice to have this common notation because you don't have to write set brackets, and it makes things look nice and tidy. So what is the point of having this pair of sets of formulas? Well, it turns out that this is a very useful logical construction if we give this a particular meaning. And the meaning of the star is we do want to read this as an implication. So if we want to understand what a sequent says, so like a logical formula states a property, a sequent states a property, and the property it states is that the conjunction of the formulas on the left implies the disjunction of the formulas on the right. So the meaning of star, and we give it semantics as we will later. So the meaning of star means, put that in inverted commas, means that conjunction of the formulas on the left implies. So we'll have to be careful. Throughout the course, I've been using the single arrow for implies, and today it's going to be particularly important that we distinguish between the logical connective implies and this notation here, which is literally just constructing a pair. That means this. So it implies the disjunction of the formulas on the right. Okay. And the rules are going to manipulate these sequences. So to introduce you to the rules, I'm going to start by giving a very simple proof. and then as I give the proof, I'll give the proof on one board, and I'll write down the rules that we're using on the other board, and then I'll expand rules with more rules until we've got a fairly complete set. And then we'll do another example proof. So let's suppose we've got a unary predicate P. And a constant C in our signature. And I'm going to give a proof, which goes like this. So what I call the identity rule. And the identity rule says it's an axiom. That's a rule that has no premises. Oops, sorry, there should be a C in here. For any formula A, I'm going to have the schematic rules here. So like in the Hilbert system, we had schematic rules like modus ponens. Schematic rule, line 10. Any instances of formulas of the relevant shape. Here we're going to have the basic schematic rule, the axiom. It's called identity. And it says that any gamma and delta and formula A, we can always prove this sequent here. So A implies A, if you like, but it's actually the conjunction of gamma and A implies the disjunction of delta or A. But anyway, you can hopefully clearly see that that's a logically valid property. And so we're applying this in the case that the side formulas, these formulas here at the side are called side formulas, but there are no side formulas. So here we've got the case in which gamma and delta are the empty set. Then we're going to apply the rule for negation on the right. And the rule for negation on the right is called negation right. And what it gives us is a way of deriving a sequent that has a negated formula on the right-hand side. And we can derive that if we can prove this sequence here, in which the formula A is moved over to the left and the negation doesn't appear. And it's kind of saying if gamma and A implies delta, the soundness of this rule is basically from if gamma and A implies delta, then gamma implies not A or delta. You can read the sound, understand the soundness of the rule like this. And that allows us, using that rule, we can bring the left-hand formula here over to the right of the sequent, and we get negation of BC, BC. So here we're applying negation on the right. And now we're going to apply a rule disjunction on the right. And disjunction on the right allows us to prove a sequent that has a disjunction on the right-hand side of the sequent symbol. And to do this, well, we can simply remove the disjunction symbol. And we take it, so here we have one formula and we replace it with two formulas, but each of those two formulas is smaller than the formula we started with. It's a sub-formula of the formula we started with. So, okay. So this allows us to derive using negation on the right. Well, this is a set, so it doesn't matter what order these things are in. So we get PC or not PC. Okay? And we've proved an instance of the law of the excluded middle. So this system is already classical, even with these three rules here. And actually, there's nothing special about PC here. I just wanted to emphasize that this is for a particular formula. But of course, we have a corresponding schematic proof where you can perfectly well, for any formula A, you've got exactly the same thing that you can derive. The identity gives us A, the sequent A on the left, A on the right. Doing negation on the right gives us not A, A. And doing disjunction on the right gives us A or not A. Okay, so this is a schematic proof of the law of excluded middle. Okay, so these are examples of the rules. One of the nice things about sequent calculus is that the rules are very disciplined. Going to be talking about a particular connective. And for every connective, we're going to have a rule that allows us to derive a formula with that connective on the right of the sequent, and another rule that allows us to derive a formula with that connective on the left of the sequent. So for negation, negation is a sort of symmetric operation. So for negation, the left rule allows us to derive a negation on the left of the sequent. But it's actually we just do the opposite thing to this, but for the premise, we put A over onto the right-hand side and again remove the negation. On the left, in order to prove a sequence involving a disjunction on the left, we need to prove two premises, one in which we have just A on the left, and one in which we have just B on the left. And this is intuitively understandable in the following way, which is from our experience in mathematics, we know that if we need to prove that a disjunction implies something, that the disjunction A or B implies delta, well, to prove that, we need to show that both A implies delta and B implies delta. So we have two proof obligations in that case. And the rules for conjunction, that's and, are pleasingly symmetric to the rules for disjunction. So we have a rule on the left, which, because the comma on the left is interpreted semantically as a conjunction, if we've got two separated premises on the left, separated by a comma, it's equivalent to having them putting a conjunction between them. So that allows us to prove a sequence where we've got a conjunction on the left. And then for conjunction on the right, well, to prove a conjunction, we need to prove both parts of the conjunction. So it's like the dual rule to the disjunction on the left. We again split the conjunction on the right like that into its two parts, and there we go. And maybe I should just give the rules for implication as well. So implication is like a form of disjunction, only the left-hand side is negated. So to prove, so to prove a sequence in which you have an implication on the left, we have two premises. one involving B, that's not negated, so it stays on the same side of the sequence symbol. And the other involving A, that's like negated in the disjunction reading of implication. So that goes over to the right-hand side. Sequent. I should give these names. So this is all left, and right, implies left, implies right. So implies right is to prove A implies B on the right. Well, then we put A over to the left. And we have this goal here. So you can kind of, it's not exactly the same because we're not making assumptions, we're proving sequence, but still you can understand this a bit like the natural approach to proving an implication. In order to prove an implication, you assume the antecedent and derive the right-hand side of the implication. Okay, so this should be implies on the right. And then we've got, I suppose we should also do the logical constants. So false has just an axiom, which is you can always derive a sequent where false appears on the left. And that's basically implementing the fact that false implies anything. We call this bottom on the left. And there is no rule for proving a false on the right, because you never want to prove that false holds. And this rule for false, together with the fact that there is no rule for false on the right, is the natural instance of this rule. This rule you can generalize, and these two rules for disjunction you can generalize to arbitrary k-ary disjunctions. And then in the case that k equals 0, the 0-ary disjunction is false. And in the case that k equals 0, you get that there should be no rule on the right, and you get this rule for the rule on the left. So then we have quantifier rules. So again, we're going to have right and left rules, both for the existential quantifier and universal quantifier. And again, there's a sort of duality between existential and universal quantifier, similar to the duality between disjunction and conjunction. So let's do the universal quantifier first. So to prove universally quantified formula on the right, well, we're going to take the approach that to prove a universally quantified property, you prove that the property holds for an arbitrary x. So like the generalization rule in the Hilbert system. And we can do that. We simply say we just need to prove the sequent where we take the universal quantifier off, as long as this x does not appear free in gamma and delta, because that means that if we can prove this property for an x that does not appear free in gamma and delta, then we're essentially proving it for an arbitrary x. And I seem to be writing a turnstile here. It's supposed to be the sequence symbol. People often write turnstiles. So let's write side conditions. So everything above the line here are actual premises. They're sequence that you need to prove in order to be able to derive the conclusion. But here there's a side condition, which is that x does not belong to the free variables of gamma and delta, of the formulas from gamma and delta. And to prove a sequence in which you have a universal quantifier on the left, then it's enough to prove any instance of A for any term substituted for X. So one thing I want to emphasize at this point, because I've had many oral exams where people tripped up on this, is that it's really essential here that we're just taking the universal quantifier off, and we've got a variable appearing. So X is a variable, and it doesn't occur free in gamma and delta. Whereas in this rule, it's really essential that you can use you're allowed to substitute any term in. Because in order to show something follows from an assumption that, so delta follows from the assumption that A holds for all X's, it's enough to show that delta follows from any single one of the instances. And the rules for the existential quantifier are completely symmetric. So to prove an existentially quantified formula on the right, then it's enough to prove any term substitution. And to prove, so this is all on the left, and to prove that something follows from an existential quantifier, so to prove a sequent with an existentially quantified formula on the left, then again we simply prove that we remove the quantifier, but we need to be showing that delta follows from an arbitrary X for which A holds. So once again, we have the side condition that X must not occur free in gamma and delta. So X does not occur free so it's not in the free variables of gamma union of gamma. So gamma comma delta leaves the union anyway. Okay, so those are so the main logical connectors. I didn't do true, but true has a right rule but not a left rule, and you can see the notes for that. So we'll compare it to the Hilbert system in the next, after the break. I think I want to end this part with just one more example of a proof. And I'm going to prove the following. So what I'm going to do is we're going to prove the validity of exists X. So P is again going to be a unary predicate. Exists X, Px implies for all Y, Py. And by proving this, I mean we're going to prove the sequence that has just this formula on the right-hand side. So has anybody seen this formula before? Do you know what it's called?
Drinker's paradox.
Yeah, the drinker's paradox, or the drinker's, I don't like to use the word paradox when things aren't paradoxical, or the drinker's formula. So you read it like this: P is, if you like, so P was appropriate. So you read P as stating that X drinks, and you're in the model of a pub, and the formula is stating that in the pub there exists, the validity says whatever pub we're in, there exists someone such that if they drink, then everyone else drinks. So that person is like the life and soul of the party, so to speak. And I want to prove this formula because you may know this it's fun to think about why this is valid. It's a famous formula in classical logic, but so you can prove this in any complete proof system for classical logic. However, I challenge you to write down a proof in the Hilbert system. Of course, in the Hilbert system, you have to convert the existential quantifier into a universal quantifier because we only have Hilbert systems only dealing with implication and false as we did it, and the universal quantifier. Anyway, you can do that, and the proof is very long. So, of course, there are other nicer proof systems than the Hilbert system, such as natural deduction, for example. But I also challenge you to write down a proof of this in natural deduction. It's quite complicated. Whereas in sequent calculus, the proof is beautiful and elegant and illustrates also a good point. So let's do that. So if you want to, one of the nice things about proofs in sequent calculus is it's not so hard to construct them compared with the Hilbert system. And to do that, you work from the conclusion backwards, trying to find a proof. So we're going to try to prove the sequent that there exists an x such that px implies for all y py. Well, there's not much we don't have much choice at this point because we've got, you notice, every rule determines what formula you're working on. And we've only got one single rule that we could possibly use for deriving an existential quantifier on the right, and that's the existential quantifier on the right rule. So we have to use this rule, but we need a term to substitute in, and actually, we'll just use the variable x itself as a term. So we'll prove px but actually this formula is not valid. So we can't prove this one. This one we've got here. If we put in the universal, say for all x this holds, and that's just simply not valid. That's not valid. So it looks like we might be stuck. We've tried to use this, but it doesn't seem to work. But we're not. Does anyone know the reason we're not?
Because we need to substitute an actual term into this.
Well, actually, the term x is correct. So x is a variable, so it's a term, but x will work. That's a good guess, but not the right guess in this case. Is actually, we're using this comma to mean set union, and there's nothing to stop exists xa appearing in delta. So actually, in this case, we need to keep this formula around. And it's still a legitimate application of this rule, because then we have exists xa in delta. And so here we have exists xa, exists xa, but this is a set. So we just have, okay. And this is really important. So when we apply the rules, we work on this formula, but we sometimes have to keep the formula around.
Excuse me, can I?
Yeah?
Yes, so the formula you wrote down, it seemed very weird to me, because if we could proceed to the previous step just with this formula, then when we constructed the whole proof, we would also construct the proof that
yes, exactly. So that's why we couldn't possibly leave it at that, because we wouldn't be able to complete the proof. But we can still. So it looks like we haven't improved matters for ourselves, but actually we have, because what we can do now is we're going to work with this formula. And after we've worked with this formula a bit, we'll find a suitably chosen term that we can use for this existential quantifier, and then things will work out. So we work with this formula, and of course this is an implication on the right, so we're basically forced to do implication. So let's write the rules down. So here we have exists on the right, here we have implies on the right. So here we have px from px. On the left of the sequent, we have for all y py on the right of the sequent, and there exists an x px implies for all y py. Now we've got a universal quantifier on the right, and y does not appear free in any of the other formulas. It appears here, but it's bound. So we can just remove the universal quantifier. By the way, if y did appear free, well, then we would just rename this to for all z pz. Okay, because we allow ourselves to rename all throughout the course. We've been allowing ourselves to rename bound variables, and we don't see it as changing the formula. And then we would use the formula that involves a variable that does not appear free. But anyway, y does not appear free, so we can stick with the y, and we get px on the left, py here, and exists x. Px implies all y py. Now I just need to check. I'm pretty sure we use going to use the exists right. So here we used rule right. So now we're going to use the exists right rule again, and we're going to use the variable y. So we get, and now we don't need to keep the formula around because it's done its job. So, we're going to be able to complete the proof. So here we're going to substitute y in for x. So we have py implies all y py. Of course, there are. So this is exists right. There are people that believe you should never mix up free and bound variables like this, and they have a. Yeah, I think it's a perfectly good point, especially in courses at the undergraduate level and so on. But we're at the end of a master's course, so at this point we shouldn't get confused that we've got the same variable appearing both bound and free here. So now we're going to do implies on the right. So we have px, py, and for all y py. And we actually never even needed to really look at what this for all y py says in this particular case, because we're done, because we have one formula the same formula appearing on both the left and the right of the sequence. So here we have, so this was implies right. We're applying it to this formula. Of course, it doesn't, as I say, we've got sets of things, so it doesn't matter where the location of the formula is in the set of formulas on the right. And here we've got the identity rule. Okay.
Using the right exists rule, the second time we use it.
Yeah.
I don't know if I mix things up, but it says there that x can't be free.
But the exists. Sorry. Oh, this is left here.
Yeah.
So the exists right rule. Yeah, sorry. So the exists right rule.
The t can appear in both gamma and delta.
No, the exists right rule doesn't have any. There are no constraints at all on t.
Okay.
No, so you can use any term. It can perfectly well appear free in gamma and delta, and it often has to. In fact, it does. It does in this case, and that's that's very important, because when you're finding a witness for an existential statement, you can use anything that you have to hand, including things you've made assumptions about, as long as it does the job. But if you're trying to prove that a universal property holds generically, then you really have to be proving it for a generic thing. Yeah, but good question. And I had mislabeled the rule. Yeah. Any other questions? There's always a life and soul of the party. that's very good. We know that, and we shall have 15 minutes break and start again at 1:15. Okay, so having seen a couple of example proofs, the second one was at least not totally trivial. We've got some idea of how this sequent system works, and so let's now compare it with the Hilbert system. We have sequent calculus on one hand, and Hilbert system. And just at a very basic level, you know, with the sequent system, I remember when I first saw it, I thought, you know, what a mess, all these symbols. Even though it's, when you understand it, it's really beautiful. It seemed like very, very heavy to have so much notation around. At an elementary level, the Hilbert system just is simple because it works with formulas, whereas the sequent system works with sequence, which is complicated. And then the style of the system is quite different in the sense that the Hilbert system had a whole lot of axioms and very few inference rules. So there's just modus modus ponens and generalization were the only inference rules. Whereas here, maybe something I didn't sufficiently clarify was when I write, here I'm writing rules, and when I write a rule with nothing above the line, it's basically an axiom. So every rule you understand as if you can prove all the premises, then you can apply the rule to the proofs of those premises and derive the conclusion. In the case that there are no premises above, that's basically an axiom because there's the requirement of proving all the premises is vacuous, so you can always just apply the rule to get yourself started in the proof. So these two rules here are axioms. And so here we've got, in the sequent system, we've got lots of rules and few axioms, whereas the Hilbert system, it's the other way around. So many, here we have many rules, few axioms, and here we have many axioms and few rules. And there's a nice conceptual advantage to the Jensen approach because the axioms really are self-evident. And moreover, the rules are also very nicely structured in that each rule is talking about just a single connective or quantifier and saying how it works either on the left or the right of the sequence. Whereas in the Hilbert system, the axioms are themselves quite complicated formulas that you have to get your head around to check that they're true. So particularly nice things here is this. So another thing about the Hilbert system was we did the Hilbert system for this fragment of the logical connectives where we were using implies, the false constant, and for all, and everything else needed to be derived from that. And although you can add axioms and rules for the other primitive logical connectives and constants, you always need to have the implies and for alls as a basis just to get the system to work. So the Hilbert system requires for all and implies and either false or negation, let's just say false, to work. Whereas the sequent calculus is very modular. You choose which connectives and quantifiers you want. and you just take the rules for those, and it works. Okay, so modular in choice of connectives and quantifiers. The reason we were using the Hilbert system was because it was easy to define. And in particular, that makes it easy to formalize when we needed to formalize it for Gödel's theorems in arithmetic. Whereas now, because we're dealing with sequence, it's a bit more complicated to formalize. So this is more complicated to formalize. But still, there's not that much in this really, because easy to formalize doesn't mean easy. And in fact, as you may have noticed, I swept almost all the details under the rug anyway. So I didn't do lots of the details in formalizing the Hilbert proof system in arithmetic. And once you've managed to understand how to code up a Hilbert system in arithmetic, actually, it's not really much more work to encode the sequent calculus in arithmetic. So there is a book on proof theory by Jean-Yves Girard, the inventor of linear logic, and in that book he presents Gödel's theorem, in which he, with quite a lot of detail, formalizes the sequent calculus directly in arithmetic. So if anyone wants to see a big formalization in arithmetic of sequent calculus, there's a place to look. And just in terms of how to work with the system, well, we found in the Hilbert system it's not always easy to find proofs. Not always easy to find proofs in the sequent calculus, just because it's not always easy to find proofs, full stop. Proving things is a challenge, but it tends to be easier to find proofs. Because you can follow the style that we were doing. You have a goal sequence that you want to prove. You look at what the formulas in it are, and you have basically for each kind of formula, depending on its location in the sequence, either on the left of the sequence or the right of the sequence, you try to see what happens if you apply the relevant rule, and you have a methodical approach to proof searching for a proof. And for this reason, sequent calculus or something like it is often the basis of computer proof assistance. I moved that rule name because it was a bit far detached from the rule. Okay, so this is everything I've got in my table. Has anyone got any other points to add? Yeah.
I think Hilbert system is older.
Oh yeah, well that's right. The Hilbert system is older, but so sequent calculus is 1930s. The Hilbert systems were from the earlier decades of the 20th century.
I feel like in sequent calculus, not only it's easier to find proofs, at least for me, it's easier to see the idea of the proof if you were doing it in natural language.
Yeah.
And sequent, because it's such like rule thing, sometimes of course you can't really see it, but I feel like if you go rule by rule, it's maybe easier than the Hilbert system to see kind of.
Yeah, no, good. So in fact, I mean, as you're aware, there's also this proof system called natural deduction, which is very closely related to proofs in natural language. In fact, natural deduction and Gensen sequent calculus were both introduced by Gensen in the same paper, and it's very easy to translate natural deduction into sequent calculus. So a lot of proofs in sequent calculus are very close to proofs in natural deduction. The sequent calculus offers that bit of extra flexibility because of this having these multiple formulas on the right-hand side of the conclusion here, which we really exploited in the proofs that we're doing, which worked really well for classical logic, and we really exploited that in the proof of the Drinker's formula. So the proof of the Drinker's formula that we gave, it's not that easy to translate that into a proof in natural language, I think. But that's a good point. So it allows a more natural style of proof. And certainly the Hilbert system does not, the proofs in the Hilbert system are not at all natural. Although once you've got the deduction theorem, you can be a bit more, you can sort of at the meta level be a bit more natural. Okay, so here we've got lots of rules, but we haven't quite finished. I mean, firstly, this course so far has been about first order logic with equality. So how do we deal with equality? Well, in the Hilbert system, we had some axioms. In the sequent system, and this is much less well known than the main sequent system, but in the sequent system, one can deal with equality in a very similar way, in that you have two rules, one for deriving an equality formulas on the right of a sequent, and one for deriving equality formulas on the left of a sequent. And the rule for the right of a sequent is just implements the reflexivity of equality. So the rule for equality on the right is that for any term, you can always prove the term is equal to itself. And the rule on the left can be given various formulations. I like the following formulation, which is a bit complicated. And it says that basically, if we've got, I'm again switching to the turnstile notation, but so if we've got an equality on the left of a sequence, so we're saying if t equals u, basically, then of course t and u should be intersubstitutable. So one way of saying that is that if we've got any sequence as the premise, which has t and u, occurrences of t and u in it, then we can derive the same, so t and u are two terms there. Then if we add the assumption that t equals u, then we have the same sequence where we swap t and u around. Okay? This is written in the notes, so which will be published eventually when they're finished. So where this square bracket notation, we already used it once, I think, earlier in the course. But what it means is we're identifying two distinguished variables. Let's say y, z and w, I think I call them in the notes. And here we've got gamma that occur free in the set of formulas gamma and delta. Here we're substituting the term t for z and the term u for w on both sides. And here we substitute in the other direction. So it's not that we're not necessarily swapping all occurrences of t and u, going from here to here. So we've identified some occurrences of t and identified some occurrences of u, and we're swapping those two. Okay. So in the notes, I have a proof of the reflexivity of reflexivity is easy. A proof of the symmetry of equality using these axioms. I think I'm going to skip that in the lecture. Also, equality is not going to play a very big role in the rest of the lecture today. It'll come back next week when we prove the consistency of arithmetic, because arithmetic has equality in. But actually, for doing that, it turns out to be better not to use these rules, but to deal with equality in a different way. So although equality can be dealt with rules on the left and right, also on the left and right of the sequence, it's not necessarily the best way of doing it. But for those of you who know a bit of type theory, kind of rules on the right, or no natural deduction, rules on the right sort of correspond to introduction rules, and rules on the left are closely related to elimination rules or to induction rules, as people, which is something else, but is also related to rules on the left and to elimination rules. And these two rules are a bit similar to this is the introduction rule for equality as a inductively defined relation, and this is not unrelated to the associated induction rule that one gets. Doesn't matter if you don't know type theory and you don't have the references to understand that, because it's not going to be very related. I mean, it's not going to be important for the rest of the course. Okay, so that's equality. We can take it in the case that we've got equality, or leave it. And next week we're going to do something else with equality. There are two more rules I want to mention. So one is an extremely famous rule of sequent calculus, which I haven't yet put into the collection of rules. Does anyone know what it's called?
Cut.
The cut rule, right. So one of the a very important part of Genson's original proof system was the cut rule, and he proved in a theorem that actually the cut rule is not necessary, it's not essential to have the cut rule. The cut rule is eliminable. We're going to go over that proof that the cut is eliminable next week, but we're going to see something about it later today as well. But still, so without the cut rule, we haven't yet understood the full potential of sequent calculus. So let's keep in black. We'll keep the equality rules because they're sort of flagging them as different, because we're not going to really consider them that much. But the next rules we are going to consider. So the cut rule has a very different form from the other rules, in that all the other rules are related to deriving a conclusion in which you have a formula of a particular kind, either on the left or right of the sequent, or in the case of the identity rule, a formula on both sides of the sequent. The cut rule says instead that in order to derive any sequent gamma delta, you can do that by introducing a formula A and proving that this sequent with A on the left and another sequent with A on the right. So one way of understanding it, which is a bit crude because it doesn't ignore, it doesn't deal with the full complexity of the rules written, is here we've kind of got A implies delta, and here we've got gamma implies A. So if gamma implies A and A implies delta, it's a sort of transitivity property, then gamma implies delta. Of course, that doesn't fully deal with the conjunction and the disjunction here, but a more complicated version of that is correct. Now, the cut rule gives you much more flexibility in how you find proofs, because so far we were dealing with, if we're trying to prove something, well, we need to work. So if we're working with a goal sequent that we're trying to prove, we need to work with the formulas we have in the sequent and find one of these rules that matches them and apply that rule. It's very, as I said before, it's very disciplined. This gives us a lot more flexibility, because in addition to that, we can instead conjure up some other formula A, whatever formula, and prove that essentially A implies delta, well, gamma with A implies delta, and also that gamma, stick A in the middle in some sense, and that gives us a new way of proving this sequent gamma delta. And it's a bit like, well, no, I'll make this comment a bit later, that one of the ways of seeing it is it's a bit like in mathematics. You're trying to prove a result, a theorem, And you can try and do it directly by following your nose and just unfolding the theorem, but sometimes that doesn't work. Sometimes you need a clever idea, and that clever idea might be some lemma, and you basically need to show sort of mathematics implies the lemma, that's this side, the lemma is A, and then your lemma implies what you're trying to derive. And essentially, having the cut rule in the system is a bit like giving ourselves the possibility of using lemmas in proofs. We're allowed to bring in some intermediate formula A and make use of that. So this is the cut rule. And as soon as we've got that, we break the property that we had before, that all the other rules enjoy the property that in order to prove a sequent, all the rules that you've got for proving a sequent are breaking down the formulas in the conclusion sequent. And so if you define the notion of sub-formula in the right way, all the formulas appearing in the proof of the sequent are sub-formulas of the formulas appearing in the goal sequent of your proof. So here we break down A arrows B into A implies B into A and B, which are subformulas of A and B. We'll then break B down into subformulas of that. Whereas here you can just put in any formula whatsoever into your proof. So Girard in the book that I mentioned before, which is called Proof Theory and Logical Complexity, it's a very good proof theory book on sequent calculus. He calls this, he says these rules embody logical purity in the sense that the meaning of the connectives is, well, the methods are pure in that one never, in order to prove formulas involving only certain connectives, you only break down the formulas into subformulas, and you never need to bring in new concepts or something like that. So that's the cut rule. And then another rule, which is something useful, is called the weakening rule. So I put it WK for weakening. And that says, whenever we can prove, if we've proved this sequent gamma, then we can prove any weaker version of it where we weaken the left-hand side by adding some more formulas, and we weaken the right-hand side by adding some more formulas to it. Okay. And these rules in blue are then all the rules for sequent calculus for first order logic without equality. And if we put the rules with black in, that's all the rules for sequent calculus for first order logic with equality. Okay. So how do we know these rules are complete? So in the case of the Hilbert system, we have this quite complicated proof of completeness for the proof of the Hilbert system. So one thing we could do is we could prove completeness of sequent calculus. Completeness of the Hilbert system. Perhaps we could just start with a more modest goal. If we don't want to get into another completeness proof for now. So maybe we can show that at least our proof system can simulate Hilbert system proofs. If we can prove something in the Hilbert system, we can prove it in the sequent calculus. So that's the next result I want to give. So that's basically the first theorem of today. And this is a purely proof theoretic theorem. What I want to do is show you how we can convert a proof in the Hilbert system into a proof in sequent calculus. So this is the theorem, simulation of the Hilbert system. Now the Hilbert system just involved, for all implies and false. So we're only going to need the rules for for all implies and false. And the theorem says that if we can prove B from gamma in the Hilbert system, so we have the notation also for infinite sets here, but because we're dealing with sequence which are finite things, I'm just going to talk about finite sets here. So this is for a finite set gamma. So if B follows from finite set gamma of assumptions in the Hilbert system, then the sequent B on the right-hand side and gamma on the left is derivable. Okay. And this is going to be a straightforward proof just by translating a proof in the Hilbert system into one in sequent calculus. And it's easy to go in this direction because the sequent calculus is a very powerful proof system. It's got, it's easier to find proofs in the Hilbert in sequent calculus. So yeah, it shouldn't be too hard to translate from the Hilbert system. But there is an interesting point that this translation raises. So the proof is by induction on the length of the Hilbert derivation, of the Hilbert proof. And then there are a number of cases. So it's by induction on the length, but we're going to break it down in terms of what rule we used how did we derive the formula B. So the first case is that B is an assumption. Now, if B is an assumption, that means in the Hilbert system, that means B is contained in gamma, and so it's immediate. We have an immediate derivation by the identity rule of sequent calculus. If B is an assumption, so B belongs to gamma, so we have the derivation using the identity rule of the sequent B from gamma. Okay. The next case is really very, very many cases. And this is, so remember when we introduce a formula into a Hilbert proof, it can either be an assumption or it can be one of the logical axioms. And we had a large number of logical axioms. So all those ones involving implications and negations, and then the ones for equality. This proof also works with equality. And also the axioms involving quantifiers. So the second case is B is a logical axiom. And then on a case-by-case basis, you basically roll up your sleeves and you use these rules and you verify that the axiom is provable in terms of you can derive a sequent that has that axiom as the only formula on the right-hand side. So for each axiom, Hilbert axiom, we can derive the sequent. Each Hilbert axiom B, we can derive the sequent with B on the right-hand side.
Are we allowed to use weakening here?
And in fact, you can do this without using, you can do this in each case without using the cut rule and without using weakening. Okay? You can always just do it using these pure rules here. Okay?
We already have weakening in the logic because of the way the identity rule is framed.
If you have cut.
So that's a very good point. So it's going to turn out that we don't need either of these rules. We don't need weakening because of the way the identity rule is framed, exactly for that reason. And the proof is really, really easy. But you do have to be just a little bit careful about if you weaken with formulas involving free variables, you then sometimes need to rename things in your quantifier rules. Okay, but that's the only subtlety. Today we're going to have a different proof set, but it's really easy that you don't need weakening. It's not at all easy that you don't need cut. But in fact, you can check it on a one-by-one basis, check these axioms. And if Gregor hadn't gone on holiday, then you might have checked some of these axioms in the exercise class next week. Yeah?
Isn't the cut just implication on the left would be equals A? And implies A.
So the cut is not, this is not an implication. This is, if we've got this sequent, which is a pair of sets, and this sequent, which is a pair of sets, then we can prove this sequent, which is a pair of sets. But if you're trying to understand why it's true, I mean, it is. So I'm not quite sure I understand.
What does the left implication rule with B equals A?
Here we've got two premises. I mean, there's no implication formula here at all.
But next to gamma, we can put a truth, right?
Oh, sorry. Oh, I see. You mean here we've got A, but then we have A implies A. So if we use this implication left rule, we then have gamma, and we've got the formula A implies A here.
So it's just true, isn't it?
Well, it is just true, but how do you get rid of it? Because that, I mean, we've got some certain formal rules to apply, and you know, if we didn't even have the implication symbol in our logic, or we didn't have the implication symbol in any of the formulas we were proving. So the point is, these formal rules you have to apply literally as they are, and indeed, as an instance of this rule, you can derive gamma A implied, if you got the premises for the cut, you can derive gamma A implies A delta, but then you still, if you want to get gamma delta, you still need some way of getting rid of the A implies A. One way to do that would be to derive A implies A on the right and cut it out, but then you'd need the cut rule to get rid of it. So do you see the issue? So
just really quickly, the reason I asked about weakening is because formally, I think it's not enough to prove like that this sequent, this last one, so sequent B, because we need the gamma sequent.
Aha,
yes,
right.
That's what we're looking
yes.
at.
So then, yeah, we don't need weakening for this, but then by weakening,
yes.
but you could also prove directly gamma that B follows from gamma. I'll stick the gamma here. But then you have to do a whole like schematic lot of proofs in a sense. So it's nice. It's kind of nicer to say for each axiom we just derive this, and then we weaken, and then we do the weakening, and then prove that you can get rid of weakening. So by weakening, but let's leave it like this for now. Follows. Okay. Anyway, you can enjoy yourselves trying to prove some of the axioms from the sequent calculus rules. So those are simple cases. There are the two inference rules. Sorry, I rubbed off with what I've just written before anyone saw it, but I think that happens sometimes. So then there are the two inference rules. There's modus ponens and necessitation. So necessitation is the rule that, sorry, is it not necessitation, that's a modal rule. What's it called? Generalization. generalization is the Hilbert rule that allows us to derive a universal quantifier. And we can derive a universal quantifier from a formula by sticking the universal quantifier in front, as long as the variable in the formula, the variable that we're universally quantifying over, does not appear free in any of the assumptions. And basically, that's exactly the condition under which we can apply the Freul-Wright rule. So the generalization rule is easily provable in the sequent calculus by the Freul-Wright rule. So I'm not going to write that case down, it's in the notes. The most interesting case by far is modus ponens. Okay, and this case is really interesting. So, case 4 in the notes, generalization. Simply use Freul-Wright rule, the induction hypothesis in the Freul-Wright rule. So the interesting case, which in the notes is case 3, is modus ponens. So suppose this is B is derived by modus ponens MP from formulas A implies B and A, where we already have proofs of A implies B and A. So by the induction hypothesis, we have proofs of the sequent with A implies B and the sequent with conclusion A from the assumptions gamma. But how do we convert that into a sequent proof of the sequent, the B follows from gamma? And well, this is not totally straightforward. So what we do is we take our proof that A follows from gamma. So we've got the proof of this sequent. The dot, dot, dots just mean we're using the proof we've already got. We weaken it on the right with B. And then we can use the identity rule to B in this form. And hang on. Yeah. And now we can apply the implies left rule. Right. The A goes up on the right here, and the B stays on the left here. I've inverted the two premises compared with what was written on the board, but that's fine. And the point is we can now use this proof and we can cut out the implies and get B here. And we can use this proof as long as we weaken it with B. So here we've got our proof of that A implies B follows from gamma. We weaken that with B. Then we apply the cut rule. And we get the B follows from gamma. So it's a bit involved, and it makes essential use of the cut rule. And that's not surprising because modus ponens is a bit like cut. We're proving B, and in order to prove B, well, we manufacture some, we conjure up some statement how arbitrarily complex that implies B, and we prove that statement. And that's when I was trying to explain what the cut rule was doing intuitively, I was using kind of metaphors similar to that. Of course, one then ends up that modus ponens is a very basic form of inference that's very natural. To natural deduction, which follows basic human inference as the elimination rule for implication. the fact that it has such a complicated derivation in sequent calculus slightly goes against the statement that sequent calculus, that I was trying to claim earlier, that sequent calculus offers a natural style of proof. This is not a very natural way of doing modus ponens, in a sense. It's quite complicated. And the cut rule is apparently being used essentially here. Later, and especially later today, and especially next week, we're going to see that the cut rule is eliminable. It's not really necessary. So why did we need to use it here? Well, the cut rule is eliminable in the sense that if we have a proof involving cut, we can always convert it to a proof without cut. But in order to do that, in this case, we would have to go into the details of what's going on here and what's going on here in these subproofs, and eventually, by cleverly working out what's happening in these two subproofs, we'd be able to stitch them together in such a way that we could get a proof of B that doesn't involve the cut. But in this modular form, we're just assuming we've got a proof of A implies B and a proof of A. There's no way of avoiding the cut if we don't want to look inside these two proofs, okay? Anyway, so that's basically that the sequent calculus simulates the Hilbert system. So we're slightly early, but this seems a natural stopping point now. So it's 4 minutes to 6. So we'll start again at 10 past 6 for the last hour. Any questions?
Yes. Can you derive meaning from the way we phrase it without cuts?
Yes. So weakening, the admissibility, as it's called, of weakening, that we don't need weakening, is orthogonal to the admissibility of cut. You can consider the two independent of each other. If we don't have cut in the system, weakening still admissible. And there's basically a very simple proof that weakening is admissible. You just stick you look at your proof of gamma and delta, and you just stick gamma prime and delta prime by the side of all the sequence, and it goes through, except that you have to be a little bit careful about three variables that occur in
but there's no like one way of like with inference rules, you just have to do it by induction to formally prove that you could derive weakening from the
you have to prove it by induction on the derivation. Yeah, you have to do it like that.
It's not directly derivable from the given inference rules. You have to do induction on the derivation.
You have to do induction on the derivation. Yes, that's one way of doing it. We're going to actually give a different proof in the last hour. But the different proof is also going to show that cut is eliminable. So, I mean, the fact that weakening is eliminable is kind of very simple, because one can transform the proof in that way, but it does need to be proved by induction and derivation. But cut is eliminable, it's much more complicated. But, now, other questions? So maybe we'll start at 13 minutes past instead. Starting with a clean board, because I want to use up more space on the boards than was being permitted by having the rules always there on the right-hand board. Hopefully we've now internalized the rules, so we can remember them when we need to, and I'll remind you as we go along. So the last thing we did was we showed we can simulate proofs in the Hilbert system using the cut rule to do so, and that gives us a kind of completeness, because we know that the Hilbert proof system is complete for deriving consequences expressible in formulas of the Hilbert system, and so the sequent calculus proof system is also complete for those consequences. But we can also formulate a more direct statement of what it means for the sequent calculus to be sound and complete, and that's what I want to do now, which is that we have this semantics of sequence, a sequent means the conjunction of the left-hand side implies the disjunction of the right. And the natural notion of soundness and completeness is that we can prove a sequent if and only if that implication from the disjunction to from the conjunction to the disjunction is valid. So this is the statement of soundness and completeness. And completeness. Or equal calculus. So on the one hand, we've got for any sequent, finite sets of formulas, gamma and delta, we have the statement that the sequent gamma on the left, delta on the right is provable or derivable, I shall say, in calculus. And then we've got an if and only if, or this holds if and only if the sequent is valid under the expected interpretation. And of course, the right-hand implication here is going to be soundness. Provable implies valid, and the left and the right to left. So the left to right is soundness, and the right to left is completeness. But we need to say what valid means, and so that's. But if you like, it's the validity of an implication. But since we're involving formulas, we've got free rather than sentences, we've got free variables there. Let's just state directly what this means fully semantically in terms of structures. So it's for all structures M, curly M, and environments rho. If the conjunction of the left-hand formulas holds, in other words, if for all A in gamma, A is true in M under environment rho, so that's saying the conjunction of the finitely many formulas in gamma holds, then the disjunction of the formulas in delta holds. So then there exists some B in delta such that B holds under the environment. Okay. And because this one in particular is quite a lot of symbols, let's give ourselves a notation for this. So for this, I'm going to overload, even though I said we didn't want more overloading at the start of the lecture, but I'm going to overload the entailment symbol or satisfaction symbol even more by putting a subscript seq on it. And so this means this gamma entails delta, where gamma is interpreted as a conjunction and delta is interpreted as a disjunction. Okay. And here we're going to have an analogous notation using the proof theoretic version of this, the consequent symbol. So here we're going to write gamma and delta. So delta is derivable from gamma. The sequence sense, meaning this. Okay. So as always, soundness is proved by an induction on the height of the derivation, and you simply show that every rule preserves this property. So soundness holds because every sequent axiom satisfies this property that it's valid and this validity property is preserved by the rules. And I'm not going to go into the details at this stage of the course. I think we even skipped it the first time around. And the validity property and this property is preserved by the rules. What I do want to do is show you, we've already had one outline of a proof of completeness. I'm going to give another one using the sequent system. And the reason for directly for the sequent system, and the reason for doing this is there's a very elegant proof of completeness for the sequent system. And moreover, using this proof, we can establish some rather deep facts about the sequent system. So what we're going to prove is what I call cut-free completeness. So this is a theorem. Cut-free completeness. And this says, if we can prove, if a sequent is valid, he holds the sequent, then the sequent is provable. But not just provable, it's provable without using the cut rule and without using the weakening rule. And I'm going to write CF here, and I'm going to call this cut-free provability. So it's slightly stronger than just provable without cut. It's also provable without weakening, but the fact that you can prove things without weakening, as we've already discussed in the breaks, is rather straightforward. So I want to emphasize the cut-free point here. So the definition here is that gamma cut-free delta means that the sequent gamma delta is provable not using cut and weakening. Okay, without using, it'd be better to say without using cut or weakening. So neither of those rules is used. Okay. And as a consequence of this, we get the property that you don't need the cut rule. If you can prove something with the cut rule, you can prove it without the cut rule. And if you can prove something with the weakening rule, you can prove it without the weakening rule. We'll just state it for cut. And this theorem is called, well, let's call it a corollary, because it's a corollary of the theorem. And now I want to prove the corollary. So the corollary, so it's the admissibility of cut. So that means if you can prove the premises of the cut, then you can prove the conclusion of the cut without using the cut rule itself. If you can prove the premises without using the cut rule, then you can prove the conclusion without using the cut rule. Admissibility of cut. So well, let's even do it like this. This can be in the notes. Let's say the eliminability of cut. We'll put this corollary in that if you can prove a sequent using cut and weakening, then you can prove it without cut and weakening. So this is a purely proof theoretic statement. It doesn't involve semantics, the statement. and it's that if we can prove the sequent gamma delta in the full sequent system, then if we can prove that, then we can prove it. We have a cut-free proof of it. And it has a one-line proof. So although it's a proof-theoretic statement, we have a one-line proof from the theorem using semantics. Because if we can prove, so suppose, well, let's just write it as a chain of implications. If this holds, then by soundness, then we have that the sequent is valid. And then by cut-free completeness is provable without cut. Completeness. Okay. So it's a very nice, we're going to see that the proof of completeness is a very natural proof of completeness, and it just naturally goes ahead without the completeness, we need to prove, if we've got something valid, we can find the derivation of it in the sequent calculus. So it's plausible that it would be helpful to have as many rules as possible for that, because it should make life easier. But just the proof naturally, very naturally, goes ahead with the cut-free, works in the cut-free system. And then it falls out of that the cut rule is eliminable. And this is I think this was due to, this observation was due to Beth in about the 1940s or 50s or something, this way of looking at things. And it's really nice because we're proving a purely proof-theoretic result, and it is possible to prove this result in another way, which is to take a proof using the cut rule and do some manipulation of the proof and get rid of the cut rule by carefully manipulating the proof. And actually, this is what we're going to do next week. This was one of the big contributions of Genson's original paper when he introduced the sequent calculus, was doing exactly this. This proof is what we're going to do in the first hour of the lecture next week. But it's a beautiful proof using completely different methods, but it's quite involved. And I think it's really lovely that there's this very simple modulo that we have to prove completeness, semantic argument that works instead. Right, so having said that, the remainder of the proof of the lecture is going to be a proof of cut-free completeness. So let's just get started on that. So proof, I'm going to start at the bottom of the board. Proof of cut-free completeness. So everything I've said so far works for the full sequence system, including the equality rules. Okay, all the statements work. However, the proof of cut-free completeness is significantly more complicated if one includes the equality rules. So I'm going to forget the equality rules and we're going to satisfy ourselves with a proof of cut-free completeness for first-order logic without equality. So for simplicity, and really it's a beautiful proof without equality, and if one sticks equality in, it's no longer a beautiful proof. So for simplicity, we consider first order logic without equality. So we just don't have any atomic formulas. Equalities for atomic formulas. So first order logic without equality. Yeah. And just like we did when we proved completeness with the Hilbert system, we're going to prove a sort of model existence theorem, which is a contrapositive. So we're going to show that we're going to assume that we've got a sequence that's not cut-free provable, and we're going to prove that it's then not valid. Which, in proving it's not valid, means we find a counter model to its validity. A structure that shows that it's invalid. So we're going to assume we've got a sequent that's not cut-free derivable. So suppose that, and I'm going to call it gamma 0 delta 0. I'm sorry, this is not cut-free derivable, so the negation of the cut-free derivability relation holds. And we need to prove that it is not semantically. So again, I'm crossing out this relation, which is proving that the sequent is not semantically valid. And to do this, we're going to progressively enlarge the sequent gamma 0 delta 0, throwing in more formulas, which are going to help us to construct the counter model to validity. So we shall construct infinite sequences of sets of formulas, starting with gamma 0. We're going to expand it to gamma 1, to gamma 2. So we're going to always enlarge them. And we're going to always enlarge, we're going to at the same time enlarge the deltas. So we're going to have a sequence of deltas. Throwing in additional formulas that are going to help us construct the counter model. And we're going to do this in such a way that at any stage I we're at, the sequent gamma I delta I is still not cut-free provable. We're going to maintain that invariant, that the sequent we're dealing with is always not cut-free provable. So we maintain the invariant property that gamma I, the sequent gamma I delta I is not cut-free provable. Okay. And the main clever thing to do is to construct these infinite sequences in a nice way, but you'll see it follows very naturally from the sequent calculus proof rules. So firstly, to do that, by the way, I'm assuming we've got a countable signature. I didn't say that. We're going to enumerate all formulas over the countable signature. There are countably many formulas. Moreover, we enumerate all formulas in such a way that every formula occurs infinitely often in the enumeration. And we're also going to enumerate all terms. We'll enumerate all terms first. We enumerate all infinitely countably many terms, including variables. Many terms. So just to be able to look for the smallest term we haven't yet considered, for example. Terms. And we also enumerate all countably many formulas such that, as I said, every formula occurs infinitely often in the enumeration. In the enumeration. And hopefully we can also satisfy ourselves with a logically complete set of connectives and quantifiers, so we don't have too many cases to consider. So for simplicity, let's just restrict to the same fragment that we had for the Hilbert system. So we use just implication, false, and for all as the connectives and quantifiers. The proof technique is absolutely irrelevant to the proof technique that we've restricted here. It's just to have a limited number of cases. The proof technique is completely modular. It's just to have a limited number of cases so that we stay within time. Don't go crazy with too many cases.
Excuse me.
Yeah.
Just, one question. The other rules are derivable just with the rules for these connectives, right?
Sorry, which are the rules?
Well, all of the rules that we don't use.
Aha. It's better to just think of it as the rules are modular. So whatever fragment you have, you put in the rules for that fragment. Okay, and the completeness is proved with adapt very easily. And I think that's the best way of looking at it. Right. So now we want to construct these sequences here. So suppose we've got, so given gamma I and delta I, and delta I plus 1, I, and we consider the case of the ith formula in the enumeration, and we see I let A be the ith formula in the enumeration formulas. And we look to see what form A is and whether it occurs in gamma I or delta I. So the first case is if A, this means it's syntactically identical to, so if the formula A is an implication, B implies C, and it's contained in gamma I. So in that case, we define gamma I plus 1 well, let's go to another line because we're going to need more space. So gamma I plus 1 to be equal to gamma I C together with C, and delta I plus 1 is just the same as delta I. In the case that gamma I plus 1 together with C, sorry, gamma I together with C, that this sequent, if we add C to gamma I, is still not cut-free provable. Okay, so this is, the point is gamma I plus 1, delta I plus 1 needs to not be, that sequent needs to not be cut-free provable. And we can add, so we'll add C to gamma I if doing so indeed means that it is not cut-free provable. And otherwise, so we've got two cases here. So otherwise we keep gamma I as it is, and we add B to delta I. And I'm not going to write it down, but now is the crucial point. The crucial point is that gamma I plus 1, well, let me just write it like this. indeed, it's the case that the sequent gamma I plus 1 delta I plus 1 is not cut-free provable. That's immediate if we follow the first definition here, because that's what this condition says. To go into the other case, well, we needed that this one was cut-free provable. And in that case, if it's the case that this one is cut-free provable, so we have a proof of this sequent, and if it were the case that then this one is cut-free provable too, so this one would now be defined in this way. So if we had both of these cut-free provable, so then we would have gamma I b delta I is also. So in order for this not to hold, it would be the case, would need to be the case that both these sequences were provable, were cut-free provable, in which case we could apply the arrows, the implication left rule, and we get that gamma I b implies c delta I. We got a cut-free proof of this, but b implies c was in gamma I, so this is just gamma I delta I, so we're contradicting the non-derived. This is saying that we've derived gamma I delta I, and we're maintaining the invariant that we can never have a cut-free derivation of gamma I delta I. So the point is that really what's happening is we've got that gamma I delta I is not cut-free provable. Because it's got an implication in it, we could try to derive it by an implies left rule, as we do here. And because it's not provable, one of the premises must not be provable. And if it's the first premise, then we use that to get gamma I plus 1 and delta I plus 1. If it's not the first premise, then it must be the second premise, and we use the second premise. So that's the main idea into here. We do something similar for if, so case A is B arrow C in delta I, something a bit similar, but easier. So I'll omit those. There'll be full notes on this. Notice that only one of these two cases can hold, because if the same formula were in both, then gamma I delta I would be cut-free provable by the identity rule. Only one of these two cases can hold. So the next case, the next two cases are if A is a universal quantifier in gamma I, and if A is a universally quantified formula in delta I. So in the first case, if A is a universally quantified formula in gamma I, so for gamma I delta I to not be cut-free provable, which is our the property we're maintaining, but so we've got that, that's not cut-free provable. So we know we can't derive gamma I delta I by means of a for all left rule. So for any term, if we substitute the term for B, because the for all left rule involved the substitution of terms, it's safe to add it to gamma I. So in this case, we define gamma I plus 1 to be gamma I together with B with a term T substituted for X, and delta I plus 1 to be equal to delta I, we keep that the same, where B is the smallest term in the enumeration of terms, the first term in the enumeration of terms, such that the formula B T substituted for X does not appear in gamma I. Okay, T smallest first term such that B T substituted for X is not in gamma I. And in the case that A is the universal quantifier on the right, so now the sequent gamma I delta I is not cut-free provable. Therefore, we can't derive it by a for all rule on the right, involving the formula for all xb. So that means if we add b with a, so of course for all xb could be for all wb with w instead of x, where w is some variable that doesn't occur in gamma I delta I, and therefore we can safely add b with some fresh variable substituted for x to delta I. So in this case, we keep gamma I the same, and delta I, so delta I plus 1 is delta I together with b with, say, w substituted for x, where my w is variable, but let's choose is the first free variable, is the first variable in the enumeration, such that w is not a free variable in gamma I and delta I. And the other case is, in any other case, we just don't do anything to gamma I and delta I. If A is some other formula that isn't one of these. Otherwise, we just keep gamma I plus 1. So the same, and delta I plus 1. The same. Okay. So having done that, so it might look a bit complicated because I'm a little bit rushing as well, but it's really this idea that the sequent is not provable. So we consider all rules we could potentially use for deriving the sequent. We know we can't use them. So in each case, we know that one premise of the rule must not be provable. If all the premises were provable, we would be able to prove the sequent. And we add that, we can safely add that premise to the relevant set, either the gammas or the deltas as appropriate. We know, we've got these growing sets, gamma and delta. We now collect them all by taking the union. So let's define gamma infinity to be the union of all the gamma i's, and delta infinity to be the union of all the delta i's. So these are now infinite sets, potentially. They don't need to be. And we're going to use these sets to define the structure that we want that's going to be the counter model to validity. And we define by M by this underlying set. Because we don't have equality, we don't need to worry about equivalence classes. Because we don't have equality in the logic, we don't need to worry with equivalence classes. We can just say it's going to be a term model construction like we had in the proof of completeness for the Hilbert system. So we can simply define this M to be the set of all terms. A function symbol in the structure M applied to the right number of arguments from the structure M. These are simply terms. That's just simply defined to be the term, which is that function symbol. A predicate symbol in M applied to some parameters from M, which are simply terms. It's defined to hold if and only if the atomic formula T1 to Tk is contained in gamma infinity. The idea is we're building up formulas in gamma that are true. We're building up formulas in delta that are going to be false. And we're going to have a structure such that all the formulas in gamma are true and all the formulas in delta are false, and that invalidates validity. because validity said if all the formulas in gamma are true, there must exist some formula in delta that's true. So we've defined the structure here. We define an environment by an environment applied to a variable x is just the variable x itself. And then we have a lemma which basically proves itself given the construction that we've done. Now, when I said the notes aren't finished, the proof of this lemma is the bit that I haven't written up yet. So I was thinking when we get to the proof of this lemma that I was going to have to improvise the proof on the board, but we don't really have time to improvise the proof. So what I will do is I'll tell you how one proves it, and you can look forward, if that is the right word, to the notes being published on the web page and see the details in due course once I've written it up. So the lemma says, for all A in gamma infinity, in the structure M that we've defined under the environment rho that we've defined, the formula A holds. And for all B in delta infinity on the right-hand side, in the structure M under the environment rho, B does not hold. And the proof, as I say, I'm not going to improvise it on the board because we don't have time, but the proof is by induction, is a straightforward induction on the logical structure of A. It's an implication. It's an implication in gamma infinity. At some point, it must appear in the enumeration. At some point, because everything occurs infinitely often in the enumeration, at some point after it occurs in some gamma i's, it must appear in the enumeration, at which point we've considered the B implies C. We've gone through this case, and we've either thrown in a C into the left-hand side or a B into the right-hand side by induction hypothesis on the structure. C is true or B is false, and that's exactly what we need to get that B implies C is true. Hang on. Something's wrong. Sorry, C was on the left hand. C is true and B is false. That's a bit better. So C is true or B is false, which is exactly what we need to get that B implies C is true. So proof is by induction on logical structure of A, B. And they're proved simultaneously by induction on the
Logical structure. Syntactic structure.
Well, so you just have to be a bit careful because you're substituting terms in. So when you substitute terms in, the formula gets more complicated syntactically, but the logical structure doesn't change. So the logical structure is just the structure of the connectives and the quantifiers. Well, and once we've proved the lemma, then we're done, because that shows the so from the lemma, that gamma 0, the sequent gamma 0 delta 0 is not valid because this structure curly M is the counter model to that validity. Okay, so it was a bit rushed, but I hope you've got some of the flavour of the proof. And really, what's really nice about this proof is that essentially you can view it as you've got an invalid sequent and you're kind of searching backwards for a proof of the sequent, and you know it doesn't exist, and the fact that it doesn't exist pushes you down a branch, a branch of invalid sequence where you keep on growing the formulas on the left-hand side and the right-hand side, always throwing in sub-formulas so every formula on the left eventually gets broken down into its sub-formulas, every formula on the right eventually gets broken down into it. Information about the atomic formulas is enough to construct the model that you need. Okay, good. So that's everything for today. Are there any questions?
Maybe just the seek SE.
Ah, yes, indeed. Thank you very much. Can I give you some of my papers to read before I submit them? It's a very, very useful service.
Do you pay good money?
Sorry?
Do you pay good money? I can do it for money.
Well, there should be a pleasure factor involved in reading. Any other questions? Okay, good. Sorry, I didn't finish really early today, but never mind. I can't finish early everywhere.